All right. Good morning, everyone. My name is Erfan. I'm super excited to present our work on practical packet deflection in data centers. This work has been done in collaboration with Seper Abdous and Dr. Suda Qurbani at Johns Hopkins University. So the traffic in data centers is bursty. This is the CDF of burst durations for 3 representative workloads in a Facebook data center. What we can observe from this simple figure is that the majority of bursts are generally short because they complete in less than 100 microseconds, and they occur regardless of the workload type. So far, dealing with bursts has been a challenge for the networking community since existing congestion management schemes are not resilient against the impact of bursts. For example, congestion control protocols, if we can see the animations. Yes. So congestion control protocols try to control bursts in the core of the network by controlling the rate at which packets are sent into the network using a sliding window. So if, for example, an initial window of 4 packets is sent to the network and one of these packets are lost, the congestion control's reaction is to reduce its window size. And unfortunately, the time that it takes for the sender to notice this congestion event until it can react to it is far more than the average duration of bursts that we see in the data center. Other group of works try to address bursts at the core of the network by better distributing the load through the cluster. So these load balancing schemes rely on multiple paths that exist between each sender and receiver pair. But even when using these load balancers, multiple packets can arrive at the last hop at the same time. And if we again look at previous reports from, for example, Google here, we see that the majority of packet loss events happen at the last hop, which makes load balancers not super helpful for preventing bursts, preventing drops that are due to bursts at these last hops. Finally, we have packet schedulers and active queue management schemes that actually are aiming to reduce the queuing delays and provide prioritization for more important flows. So in this example that we have, you're looking at the traffic management component of the networking switch. A burst of high priority packets can arrive at some buffer and then overflow it. And then the scheduler has, again, no option but to drop the excess packets, again, victimizing the performance of that important bursty flow. So in order to address these issues with bursts, recent proposals in data center networking propose packet deflection. And in a few words, packet deflection mechanisms act by sending the packets that arrive at a full buffer to a neighboring switch, creating an opportunity for that packet to linger in the network a bit longer and eventually come back to its main path, hoping that the buffer at that time is not full so it can reach its destination. This kind of reminds us of those early hot potato routing schemes, and it's quite simple and effective because we can have query completion performance improvements of up to 43 times. But unfortunately, the existing deflection mechanisms are not implementable in existing programmable hardware. So let's see why. These state-of-the-art deflection proposals depend on 2 main primitives in the programmable switch for their implementation. First is the ability to filter out congested ports, because we don't want those deflected packets to arrive at a second buffer that is also full, and then we have no choice but to drop it. So at the bottom, you're looking at a typical PISA programmable architecture that consists of various stages like header parsing, ingress processing, traffic management, and egress processing. These deflection techniques need to first access queue utilization data in the ingress pipeline. And then using that data, they need to filter out congested ports and then randomly select one port and send the deflected packet to that port. Unfortunately, this is not trivial in resource-limited programmable hardware that we have access to. The second requirement for deflection mechanisms is to change the buffer of already inserted packets. So, for example, we want to extract one packet from the buffering management unit and insert another packet into that buffer. And again, this is not a primitive that is offered by any available programmable switch architecture. So in this work, we try to come up with ways that we can actually implement these deflection methods. We target existing programmable switch architectures and implement two types of deflection mechanisms, namely simple deflection and an approximation of selective deflection that we call preemptive deflection. Now we will see the difference between all these alternatives later in this talk. Our intuitions behind making deflection practical is that existing capabilities in available switch architectures like packet recirculation can safely replace expensive memory manipulation operations. And the fact that admission control policies can be combined with packet deflection to realize priority-based deflection. So you're looking at the results of our simulations in a 100 gigabit per second FAT3 cluster using DC-TCP as congestion control. The x-axis on this plot shows the aggregate network load as we increase the intensity of the incasts. And the y-axis shows the mean incast query completion times in seconds. So you can observe that our practical deflection alternatives targeting simple and preemptive deflection can closely yield the performance benefits of their clean slate, non-implementable counterparts, while both of them greatly improving over the baseline no deflection case. And we will investigate these results in more detail later in this talk. So now our discussion shifts towards different alternatives for deflection. There are in general two alternatives. The simple approach is triggered when a packet arrives at a full buffer. Then using the queue occupancy information, the switch randomly selects a non-congested port and then deflects the packet to that port. And this is very simple and works under moderate degrees of congestion. But previous works have shown that under a large degree of congestion, some problems may occur, for example, ahead of the line blocking and things like that. And that is where selective deflection comes to the picture. In selective deflection, the fabric is assumed to know packet priorities. And packet priorities can be, for example, the remaining bytes of the flows like in pfabric, or just simple flow priorities. And then the switch is able to prioritize more important flows, first for forwarding and then for deflection, to kind of provide a fast path for flows that are about to finish. And again, the practicality of such schemes is still under question, and that's what we are going to do in this work. Let's start with the simple deflection case. So you're looking at the traffic management unit of a switch with 8 ports. First 4 ports are facing neighboring switches. The other 4 ports are facing end hosts. And as I mentioned, the switch knows the queue utilization data beforehand. So if a packet arrives at a full port, what the switch does is that it looks at the other ports that are facing the neighboring switches. The first port is also congested, so it randomly selects from the other 3 ports facing the neighboring switches, selects one, and then deflects the packet to that port. And this is simple enough to prevent drops at moderate congestion, improves the overall query completion times by 71% in our experiments. But we first need to find a way to access queue utilization information not available in all switch architectures. And the second challenge is to filter the ports, which requires many compute-intensive operations in the resource-limited switch. So for the first challenge, we create a shared state between the ingress and the egress pipelines by collecting the queuing metadata using data packets and then recirculating the metadata to the ingress pipeline using data packets, using worker packets. And the data that we collect is represented as a bitmap that simply indicates if a port is full, those red ones, or is not full, those green zeros. And then our random number generation logic chooses the first non-congested port from this bitmap, as you can see in this example. And all this can be done at line rate to realize simple deflection. For implementing selective deflection, packet priorities must be involved. So again, we have our same traffic management module with packets from different priorities inserted. So again, a high priority packet arrives at a full port. What happens is that the switch identifies the lowest priority packet from that buffer, randomly chooses as the destination port for that packet, and deflects that packet to that port. And that creates some room for our high priority packet. So we can insert this high priority packet into its correct position inside the queue based on its relative priority. And we have saved the throughput of that low priority packet from stalling because of a drop. So obviously this raises a few challenges, right? The first challenge is that the queuing capabilities in most or almost all the existing programmable switches is just FIFO. So how can we do priority-based queuing? And the second challenge is that packet extraction is not offered by existing primitives. So how to address that? And the fact is that we know that an implementable selective deflection is going to have huge improvements for some traffic patterns like incasts. So we are going to look for ways instead to approximate this method. So we ask, what if we make our deflection decisions early, that is before passing the packet to the buffering unit? And this way, we can implement or approximate selective deflection using a mechanism that we call preemptive deflection. So with preemptive deflection, we define an admission policy at the head of the queue to decide for every arriving packet if we should admit this packet into the queue or just deflect it. And this admission policy works based on a dynamic threshold that is a representation of priorities that are already inside the queue. So this threshold would depend directly on the queue capacity that we have and inversely on the relative packet priority of the arrived packet, plus a tweaking knob to adjust the sensitivity of the algorithm, which altogether result in the following simple formula for our threshold. And this is inspired by previous works on admission control, which we refer to as quantile-based admission. An operational example with a queue size of 8 packets and the sensitivity parameter of 0.5 will look like this. So if a high priority packet arrives, the calculated threshold would become 7 packets, which is more than the number of packets that are already inside the queue. So the final decision would be to admit this packet. But for a low priority packet, because the calculated threshold is less than the queue occupancy at this moment, the decision would be to deflect the packet. So this is great because we can implement this using like existing capabilities such as like rolling windows and priority sampling in Tofino 1 switches. Our implementation uses 11 out of 12 available match action stages in Tofino 1. We also investigate more resource-efficient admission policies. So for example, instead of using all those priority comparators, we can map a statistical distribution to the priority of packets that are already inside the queue. And we can implement this alternative using only 2 out of 12 stages in Tofino, with a marginally less accuracy compared to the former method. And I invite you to read our full paper for that talks about the trade-offs of these implementations. So to put it all together, we introduced 3 different deflection mechanisms targeting different needs. Our simple deflection alternative is quite easy to implement and is resource light and is quite effective under low degree of congestion. Our quantile-based preemptive deflection fortifies the shortcomings of simple deflection, works under extreme degrees of load, and accurately approximates selective deflection. And we also introduced distribution-based preemptive deflection, which trades off a little bit of accuracy to achieve better resource efficiency compared to the previous method. Now, let's see our implementations in action. So our physical testbed results are gathered from a setup like this. So 2 programmable Tofino 1 switches, 4 server machines connected with 40 gigabit per second links, and reduce the queuing for per port queuing to 80 kilobytes in this example. So we generate low priority flows using iPerf from 2 servers. For the high priority flows, we use key value traffic from server number 2 towards the receiver host. Our baseline case is when we run our key value workload alone in the system. The response times in this case are around 500 microseconds on average. But when we run our low priority and high priority flows alongside each other, then we see a huge jump in the latency of our important flows, because obviously we see a lot of contention and drops in the queue. And even increasing the size of the buffer is not going to be super helpful here. But this can be partially remedied by using simple deflection, as we can now use the capacity of the buffer capacity of the second switch. And even better, using preemptive deflection results in an almost identical performance to the baseline case when we ran our key value workload alone. We also do simulations to support our physical testbed findings. So we use Omnet simulations, 2-tier lithospine topology with 100 gigabit per second links, using 40 machines total. And we use, in this example, Swift congestion control, which is a fast congestion control algorithm with quick reactions to congestion events. So we have 2 different scenarios. Both of these use 50% background traffic. On the left, we have 5% in cast. On the right, we have 35% in cast. And the baseline case here is ECMP, load balancing, which results in around 10 milliseconds of query completion times on average. Next, we have our practical simple deflection case alongside its clean slate counterpart. And you can see that under low degrees of congestion, simple deflection can have a huge impact on the performance, almost an order of magnitude lower query completion times. But as I mentioned earlier, simple deflection is not quite useful when the degree of congestion is high. So that can be remedied when we use preemptive deflection. Now, in this case, preemptive deflection can be shown that is effective in both load combinations, reducing the query completion times by 21 times in low load, 6 times in the higher load. We also implement and evaluate other non-deflection techniques, such as admission control in AIFO that was introduced in CNAM 21. And we can, as I mentioned earlier, these mechanisms are not useful for local congestion events that with a burst of high priority packets arriving at the same time to the queue. So we see a performance that is even 3 times worse than the baseline in these cases. So overall, with our 3 deflection mechanisms that we introduced, targeting simple deflection and preemptive deflection, we hope that the data center operators can use these techniques based on the degree of congestion that they experience in their clusters, as well as the resource availability and performance constraints that they might have. I invite you to read more detailed account of the performance that we could see in our full paper. I also invite you to look at our code base in GitHub. And thank you again for your attention, and ready to take questions.
Any question? Thank you for the great talk. I have one question. So whether would your technique cause any packet reordering? And then in that sense, like whether it would affect like any use cases that are sensitive to packet reordering, like RDMA? Thank you.
Thank you. That's a very good question. So Basically, what we are doing here is to just make deflection practical. So there are different methods to deflection. There is the simple deflection method, which uses the FIFO queuing capability. So very few reordering happens in that case. It's just we are saving the packets that were destined to be dropped. So that's still better than dropping that packet when we look at the performance outcome of the simple deflection. With selective deflection, yes, there is a lot of reordering. Selective deflection was introduced in CNAM 21, and it uses SRPT scheduling. So there's a lot of reordering. It requires the end hosts to have like an ordering layer to handle the reordering. What we do here with preemptive deflection is that we are reverting back to the FIFO queues instead of those SRPT queues. So we are significantly reducing the amount of reordering that we experience in the network. But overall, with the deflection, it is inevitable to have a very low degree of reordering overall.
Any other question?
So first of all, thank you for your talk. It was very, very nice. So my question is the following. I think that, so I know that another way to control this problem is to use priority for flow control, no? In which you, instead of sending back the packet, you send back an information to the other switches. Wait a moment, because I'm quite overwhelmed. So do you have a comparison with the priority flow control? And do you think that there are benefits and drawbacks with respect to this? Because priority flow control usually avoid, for example, reordering. But I don't know if you have some data about this or some. So.
Thank you for your question. So we don't have any results like that shows the performance of deflection alongside priority flow control or like compared to that. We believe that at the beginning we were targeting scenarios where we are using anything other than lossless networks. So that was the initial assumption for our deflection works.
Any other question? Okay, then let's thank the speaker.
So hi everyone. Today I'm happy to present our work related to distributed in-network computing. And this is a joint work with my colleagues from Yale University and Denmark Technology University. And today, with the advent of SDN technology, network device becomes more and more programmable. And this means that we can offload some of the computing workloads that used to run on server to the network devices. And this can be referred as in-network computing. And in-network computing has benefits like high throughput, low latency, and is able to process and even terminate this traffic at the middle of the data path. However, there is limited resources on the programmable network device. And for example, this figure mainly shows available resource on a network device, and the network functions is able to be deployed on it, but with a considerable amount of resource consumption. And for the in-network computing algorithm, they are also to be deployed standalone on a network device, but with limited scalability. And if we would like to deploy the in-network computing algorithm together with network functions, for most cases, they will run out of resources and fail to be deployed. And if we would like to look a little bit details about resource consumption of the normal network functions, and here this figure mainly shows resource consumption of an open source router, which is real router on Tofino switch. And this figure shows 4 types of resources consumed by each stage. And the darkness mainly shows the percentage of the resource consumption. As we can see, the real router consumes resources in the first 8 stages. But for the last 4 stages, the resources are totally unused. And this is for a single programmable network device. Usually for a programmable network, there are multiple different types of programmable network devices exist. And if we can jointly utilize this distributed unused resources, we can further scale our in-network computing algorithm and perform better performance. So the goal of our research is to realize distributed in-network computing. And specifically, we would like to slice and decompose a large in-network computing algorithm into segmentations, and then deploy the segmentations along all the data paths inside the network. And distributed in-network computing is an emerging field, and there are already some work discussed about it. However, none of this work can realize the distribution of in-network computing algorithm on any data path. The one most close to our goal is flat plan, and even though it is close, it is designed for a rack scale network with limited scalability, and it only supports multiple paths instead of any-to-any paths, and will affect normal network functions. So to realize our goal, we need to overcome several challenges. The first is to find a deployment strategy that is able to deploy the distributed network computing on any path inside the network and without affect normal network functions. This means that when packets go inside the network, no matter which path it is routed, it will go through all the segments in order. And also the second challenge is how we do the information sharing between nodes. And also for the node, how it can identify which feature should be extracted and which segments should be executed. And also decompose in-network computing algorithm into segments and also insert single or multiple segments into the data plan code of each network device is not that easy. And how we can streamline the process and realize an easy-to-use framework is a challenge. And for the first challenge, to find a deployment strategy, and we mainly solve it by using ILP-based DINC planner. And I would like to firstly talk about the constraints that we define in this ILP planner. And this constraints is mainly used to make sure this distributed network computing algorithm have the same functionality as it is deployed on a single network device. And the first constraint is the dependency. And we would like to make sure that for any segments, and all its preceding segments should appear at least for one time before it, no matter on any path. And we would like to also make sure the integrity of the in-network computing algorithm for any path, which means all segments should appear at least for one time. Also, the the available resource for any node should always be higher than the total resource consumption of all the segments that deployed on that node. And these are some constraints, and we can even add more constraints based on the requirement of the use case. For example, if a use case that requires the in-network computing algorithm to be finished within 5 hops, then we can add it as a new constraint. And all these constraints can be converted into equation as shown here, and the detailed explanation related to the equation can be found in the paper. After this, we would like also to make sure the deployment strategy to be efficient. And this is mainly based on the objectives that we, objective functions we define. And here we mainly shows 2 objective functions that will be useful for most use cases. And for example, we would like to minimize the total resource consumption of the deployment algorithm. And we would like the deployment algorithm to be finished within the minimum amount of hops. And more objective functions can be added based on the use case. And after we have these objective functions, we weighted sum them all to form a global objective function. And this global objective function can be used in the ILP solver to find the deployment strategy. And these objective functions can be converted to the equation as shown here. And the detailed implementation of the ILP planner can be found in our paper. After we have the deployment strategy, the next challenge is how we realize the information sharing between nodes and segments. And we use a simple in-network computing algorithm as an example. For example, this algorithm uses 2 features as the input and output F3, feature 3 as the output, and it is sliced into 3 segments. For the first segment, it uses feature 1 as the input and output M1, intermediate result 1. And for the segment E2, and use F2 as input and output M2. And the last segment use 2 intermediate results as input and output F3, which is also the output of the program. And if it is deployed on a sample topology with a deployment strategy as shown in the bottom right corner, and the problem is how we share the information between the node A and node C, since the M1 and feature 2 should be passed from the node A to node C. And the second thing is for node C, how it should identify the difference between the packets that comes from node B or node A, since for the packets coming from node B, all the segments has already been processed. So it can directly be forwarded to the output. But for the packets coming from node A, features should be extracted, and the two following segmentations should be activated and be processed. And to solve this challenge, it is mainly based on our DINC header design. And this design is transparent to the user. So which means when packet comes inside the network, this header will be automatically added to the packet. And this header is mainly used to pass information between the nodes inside the network. And before the packets sending out of the network, this header will be auto-removed. And inside this header, there are two fields used to pass information. And the first field that is important is intermediate features. And all the information that need to be passed is stored here. And another field is important is bitmaps, and it's mainly used to record which segments has already been processed and used to identify for the nodes to identify which features should be extracted and which segments should be executed. And after we deal the problem with information sharing, we would like to introduce our framework design. And when talking about framework design, we would like to firstly talk about two types of input of the framework. And the first part of the input is from the network operator related to the network. For example, the topology and also the available resources on each network device. And this input can be input as a DAC. And also another part of the input, which is from the users, which is the in-network computing program. And since the user input the program, that we assume that they have to some extent understanding about their program. So we also require the manual annotations for the program. After framework have the input, and it will firstly activate the DINC splitter module, or in other words, a DINC slicer. And in this module, it will, based on the annotations, to decompose the input in network computing algorithm into segments. And these segments will be saved for future use. And it will auto convert the in-network computing program into a DAC. And this DAC combined with the DAC of the network topology will be used in the second module, DINC planner, combined with defined objectives and constraints. The solver is able to find the deployment strategy for this in-network computing program. After framework have the topology, it will, based on a P4 generator module, to generate the data plane code for each network device. And this P4 generator module is composed by 3 submodules, including a common P4 submodule, which is responsible to generate the normal network functions for all the network device. And the standard P4 submodule is used to make sure that each segment is placed or inserted to the right place. And the P4 generator submodule is used to make sure that the architecture used on each network device is correct. And after we have the code for each programmable network device, the framework will also auto-compile and the program and initiate the testing environment, and also load the code to each node for testing. And the DINC framework is an automated framework, which means after it have all the input and configurations, the process can be done automatically with single click. And the framework is also a modular framework, which means that if we would like to add new design, or if we like to add support to new hardware device, then we can simply realize it by adding a new module. For example, if we like to change a design of the planner, and we can do this by simply add a new planner module. And I would like to also talk a little bit detail about our slicer module, since we require the input as markers in the input in network computing program. And these markers include the information related to the partitioning and the dependency between segments, and also the location used metadata and resources on each part of the code. After we have the framework, we evaluate it on 2 types of topology. And one is a cost data center topology with 33 nodes. And another is relatively larger, which is British Telecom network topology with more than 1,000 nodes. And we evaluate the DINC framework in a range of in-network computing programs, which includes telemetry, load balancing, and different flavors of machine learning algorithms. Although this algorithm is able to deploy on the network device alone, but when it coexists with network functions, most of them is failed to deploy. But with the help of our DINC framework, the distributed deployment of this algorithm are able to coexist with network functions on both topologies. And then we also evaluated the throughput with the help of sample in-network random forest algorithm. And this algorithm is sliced into 4 segments. For each segment, it has coexist with normal network function, which is the open source real router. And for each segment, we can see it's able to run with full line rate, which is the same as the standalone deployment of this standard network function. And we also compare our result with the state-of-art result of flat plan. And in terms of the number of nodes consumption, we can see on a relatively small and symmetric topology, DINC have the same node consumption as flat plan. But with the larger and more complex topology, the BT topology, DINC can help reduce around 60% of nodes to realize the distributed in-network computing. And for the number of hops to finish the computing, DINC have the same performance as flat plan in both topologies. And for the number of used duplication of segments, and we can see in the data center topology, and the DINC can help to reduce around 35% of duplication in segments. And for the BT topology, DINC is able to help to reduce around 80% of duplications. So in summary, in this research, we are working on finding a simple, efficient, and extendable solution to realize distributed in-network computing. And our proposed DINC framework is able to handle this distributed in-network computing task on any-to-any path inside the network, and which is able to coexist with normal network functions and will not affect the normal function of these functions. For example, will not affect the normal routing. Currently, DINC framework is open available, and you can access the framework repo via this QR code. And we also provide a detailed README and getting started tutorial in the repo. And additionally, details related to the implementation of the DINC framework can be also found in the paper. And that's all for this presentation. Thanks. I'm happy to take your questions.
Thank you very much. Any question?
Yes, I didn't read the paper, so maybe I missed some points in the presentations as well. So are dealing with stateful network functions, and how do you deal with the packet loss or reordering?
Since I don't think for the distributed network computing, especially for our target program, the reordering and packet loss will affect a lot. Since if the packet is lost for the standalone deployment, it's just still lost. Or if there's the reordering in the standalone deployment of this algorithm, it will also be a problem. So for our deployment algorithm, if the standalone deployment can handle the packet loss and reordering, then the distributed version should also be able to handle it. And specifically, our support algorithm is mainly focused on the type of without, for example, without stateful or like without the use of the like or state for without like recirculation or multicast or like stateful memory, something like this.
Okay. Well, I should read the paper first, and then we can talk.
Any other question?
Hello, I see you defined how say a packet header. So where do you put this network header inside the packet? Layer 3 or layer 4? Where? Thank you.
Currently, it is in our current design. It's just after the it can be varied based on the in different networks. Currently, we can place it after the Ethernet header or after the IP header. So it is just based on the design of your network, and it can be changed based on different type of network.
So basically, you need to modify the chipset to parse the packets because you introduce a new network header, right?
Excuse me.
I mean, if you introduce a new network header, you should change the chipset to parse the packets.
Yes.
Is it correct? Okay.
Yes.
So, have you ever considered to introduce the network header into the IPv6 extension header?
Sorry for the question.
I mean, do you introduce this network header into the IPv6?
We haven't considered about the difference between
Okay.
IPv4 and IPv6.
Thank you. Maxi.
Any other question? Actually, do have a question. I'm just curious about one thing. So for the slicing, right? So I know you rely on the annotation of the program, and this makes a lot of sense because it makes everything much easier, right? So that's fine. I wonder if you have any thought on how hard it would be to do it automatically without any annotation. I know you haven't done that, but it's just, it's just, out of curiosity.
Yes, it will have challenges if we do not add any markers. And actually, it can be to some extent realized with the help of the modification on the compiler. And they do have some work doing this. But actually, the problem of this type of solution is that for any user, then they need to change their own compiler on their environment, and it will introduce additional context to the use of the framework and like this.
Okay, thank you very much. Then let's thank the speaker again.
Hi, everyone. Thank you for joining this presentation. Today, I will present our latest work entitled Millions of Low Latency State Insertions on Programmable Switches. And this is a joint work between KTH University in Sweden and Roma Tre University in Italy. So, network function virtualization is an essential paradigm of today's networks, and data centers operators manage and build complex processing pipelines by combining network functions deployed inside the infrastructure. So, deciding where to deploy these network functions is a crucial task for network architects. Lately, there has been a trend of offloading network functions into programmable switches, and such switches are high performance since they can process millions of packets with nanoseconds of latency, and thanks to their programmability, they can be flexibly updated without additional costs to support new requirements. Moreover, they are well known to be energy efficient, and they are much more energy efficient compared to dedicated hardware or commodity servers. Most of the network functions are stateful, and so they need to store and update a data structure, usually in the data plane, that keeps a state needed to process packets. And to give some examples, a load balancer needs to store the egress port associated to each flow, or telemetry network functions need to store and update counters or more advanced data structures. So stateful network functions store their state into key value data structures, and usually the key is the flow 5-tuple identifier. In programmable ASICs, the key value data structures are implemented using match action tables. And in today and even next generation ASIC switches, support for lookup operation, there is a support for fast lookup operations from the data plane, but they depend on the slower CPU-based control plane to perform modifications on these tables. And this has indeed two drawbacks. The first one is that the control plane cannot perform many operations per second in the order of 100K per second. And the second one is that such operations are slow with up to 1 millisecond of latency. So what are the implications of these problems? So let's take as an example the flowlet network function. And this network function selects an outgoing port for a burst of packets, and each burst can be forwarded to a different port. So now let's consider to run the flowlet network functions on a programmable switch. And for simplicity, we assume that it receives only 1 kilobyte packets. So we have this figure, and we consider 3 different distribution of packets per flow, and we vary the input throughput in terabit per second, and we estimate the number of insertions that flowlet should perform on the switch. So with the 300 packets per flow, the switch would require about 10 millions of insertions per second at 25 terabit per second, which is a reasonable bandwidth for today's switches. While reducing the number of packets per flow, the number of insertions dramatically increases, reaching about 60 millions of insertions per second with 50 packets per flow, which is clearly unfeasible on today's ASICs. So an alternative approach is to implement the stateful network functions using probabilistic hash tables that store the state inside the data plane. And these data structures support data plane speed operations, but they have hash collisions which can dramatically impact the performance and resource utilization of switches. So for example, let's again consider the flowlet network function running in a small closed data center emulated using NS3. And we consider 2 flowlet implementations, one using a key value and one using a hash table. In this figure, we vary the size of the data structure in both implementation, and we measure the 99th percentile flow completion time. As it is possible to notice, the hash table obtains the same flow completion time value by using 65 times more switch memory compared to the key value implementation. And this demonstrates that the collisions are not negligible and proves that the exact key values are more well suited to implement the stateful network functions. So we would like to combine the collision freeness of the key values with the performance of the data plane hash table. So in the following, we aim to answer the following question. That is, can we implement a key value data structure entirely in the fast data plane of an ASIC switch? So there are 2 main primitives in the data plane that we can use. The first one are array registers that are a stateful memory that can be read and written at data plane speed, and hash functions. So with these 2 ingredients, what we can do is that we can build hash tables. But in this work, we go a step further, which is building key values using hash tables as a foundation. So since the array registers play a key role in our implementation, we need to understand what are the constraints in current ASICs. The first one is the single access, which means that a packet can only access a register once while traversing the pipeline. And the second one is the dependency, meaning that if a register R1 is accessed before R2, then R2 cannot be accessed by R1 by any other packet. With these 2 constraints in mind, let's see which hash data structure is suitable for our goal. Indeed, the lookups are the most important operations, and so they should be supported in constant time. So the simplest hash data structure that we can think is the chained hash tables, but the lookups may require to iterate over the whole bucket, which require linear complexity in the worst case. Another data structure is the linear probing hashing, which performs lookups in constant time, but it requires to access 2 consecutive elements in the array, which breaks the single access constraint. Conversely, we have cuckoo hashing, which performs worst case constant lookup by accessing 2 independent arrays using 2 distinct hash functions. And so this satisfies all our requirements, and it is implementable in a data plane of a programmable switch by using arrays, registers, and hash functions. So this is our foundational data structure to build the key value. So aside from the constant lookups, the cuckoo hash tables handles insertions and collisions using a clever mechanism called the cuckoo approach. So let's consider the insertion of a value, in this case 66. So the first thing is that the hash of this value is computed using the first hash function, and this points to a slot into the first table, the table T1. And in this case, 66 is inserted into that location. If the slot is empty, the operation terminates. Now let's consider another value, in this case 42, that points to the same location of 66. In this case, the previous value gets removed and causes a so-called swap on the second table. So now 66 is then hashed with the second hash function and inserted in T2. If the slot is not empty, the operation repeats until all the insertions are successful. So if this condition is never met, the process stops after a predefined threshold, and the hash tables, the tables are then rehashed using different hash functions. So after this brief overview about the cuckoo hashing, we can go back to our main idea, which is use this technique to build data plane key values. So we have our two tables, and for each entry we store the value and the flow 5-tuple identifier. What we do is that we plug this structure into the data plane, and this is switcheroo, our contribution. So after presenting the idea, we immediately have two questions, which is the first one is after a lookup fails, a switcheroo needs to perform the insertion of the state into the first table, but it has been already accessed to perform the lookup. So how can we support this without violating the single access constraint? Moreover, we know that swap can occur, and while the ones from T1 to T2 are compatible with the dependency constraints, the one from T2 to T1 inherently break this partial ordering. So how can we still perform the swaps without violating the dependency constraint? For supporting both operations, we leverage on the recirculation capabilities of programmable switches, which is, we know that recirculating a packet means that it can be processed as second independent time by the switch. So a key challenge introduced by the recirculation is that it's not an instantaneous operation. So the switch could take up to hundreds of nanoseconds to reprocess the same packet. And in the meanwhile, other packets could be received by the switch. So this introduces three main issues. The first one is inconsistency. So what it means is that if transient states during the recirculation are not handled properly, the packets traversing the data structures may assume that a new state must be created. And so what happens is that a state for a single flow may end up in both tables simultaneously. Another issue introduced by the recirculation is that packets could be reordered. The switch guarantees that packets are processed sequentially inside the pipeline, but the recirculation may break this property since the recirculated packets are treated as new packets. So let's illustrate this situation with an example. So consider a new purple flow arriving at the switch, and the packet first performs a lookup that fails, and then it gets forwarded to the recirculation port to perform the insertion. In the meanwhile, another packet of the same flow arrives at the switch and also fails the lookup and gets recirculated. So at this point, the first packet performs the insertion and gets forwarded normally. But while packet 2 is still recirculating, a third packet arrives that succeeds the lookups and gets forwarded before packet 2, leading to a packet reordering. So avoid packet reordering is crucial for any packet processor since it leads to retransmissions, increased latency, and jitter on the end hosts. So the third problems are infinite loops that, as already mentioned, could be triggered by a chain of swaps and insertions that never terminates. And we discuss this problem more in detail in the paper. So switcheroo tackles these challenges and solves them by satisfying three main properties: consistency, packet ordering, and termination. As for consistency, we add an additional data structure which we call transient states that keeps track of the in-flight swaps. And this is a countable Bloom filter, meaning that it cannot return false negatives, but different flows can collide on the same entries, causing them to detect a false positive swap. But we keep a conservative approach in switcheroo, and so we treat it as so. Switcheroo implements the packet ordering relying on a really simple idea. The switch starts to sequentially number all the packets of the same flow that arrive at the switch, and then it enforces packets to leave the switch in the correct order by checking what is the next packet number that should be forwarded. And we implement this mechanism using 3 additional countable Bloom filters, ordering, packet counter, and the next packet. And each entry in ordering keeps track of the in-flight insertions. Packet counter assigns a monotonically increasing identifier to each packet, and the next packet keeps track of the next packet that should be sent out. So consider the same example that I showed before, and a packet of the purple flow arrives at the switch and fails the lookup. We append some metadata to perform the insertion. Before being recirculated, it increments the ordering entry by 1, and we assign a unique packet counter, which is 1 in this case. So it gets recirculated, and another packet arrives and fails the lookup. But this packet, as before, should perform the insertion. But since the ordering entry is equal to 1, we know that there is an in-flight insertion from a previous packet of the same flow. And so it gets transformed into a lookup, and we also assign a packet counter of 2. So now the purple flow, the first packet of the purple flow inserts the state, and now the insertion is correctly processed. So we decrement the ordering entry by 1, and the packet can potentially go out. But first we check if the value inside the next packet entry is equal to the packet identifier assigned to this packet. In this case, it's true, so it can be sent out. Now, in the meanwhile, a third packet arrives, and this performs a successful lookup, and we assign a packet ID of 3. So this also could be potentially ready to be forwarded, but checking the next packet value, we notice that this is not the right packet to forward. And so it is sent back to the recirculation with some metadata to signal to wait for its turn. At this point, the packet number 2 performs a successful lookup, and it gets forwarded since the next packet value is equal to 2. The value is then updated to 3. We have the packet 3 now does traverses the pipeline, but skips the lookup since it already has the value assigned, and so checks the next packet. In this case, the values are equal, and so it can be safely forwarded. So with this small example, we demonstrated that switcheroo forwards packets of the same flow in order. And as for consistency, we rely on a conservative approach, meaning that there could be some unnecessary interflow ordering. So to support the termination, as in Cuckoo++, we add an expiration timeout to each entry. And in this case, the loops will start to break when entries start to expire. So for more details, check our paper, where there are also the formal proofs of each property. So now let's dive into the evaluation. We implemented the switcheroo on a Tofino switch, and the implementation spawns 2 pipes, one for the Cuckoo tables and one for the additional data structures. And as use case, we implemented the flowlet network function using an expiration timeout of 50 microseconds. This Tofino is connected to another Tofino that multicasts incoming traffic, and the traffic is generated by an external server connected to the multicast switch, and all the testbed is wired at 100 gigabit per second. So to evaluate the switcheroo, we generate 3 types of synthetic traffic. The first one is one packet flows, in which all packets belongs to different flows, and so each packet performs an insertion. This is the worst case. Then we have 2 packet flows, where flows consists of 2 non-consecutive packets within 50 microseconds, triggering an insertions every 2 packets in average. And we have 8 packet flows, where the flows consists of 8 non-consecutive packets within 50 microseconds. And for these flows aligns with the average number of packets per flow in a cloud data center. So we start our evaluation by examining the insertions per second. So how many insertions per second are supported by switcheroo. We measured it by running the implementation with the cuckoo hash table size set to 32K entries. And we varied the input throughput in gigabit per second, and we measured the number of insertions per second. So switcheroo effectively performs insertions at line rate, reaching 50 millions at 400 gigabit in the one packet flow case, which is the worst case. And comparing this result with the 100K insertions per second from the control plane, the level of achieved performance is 500 times higher than the state of the art. For this experiment, we also considered a real-world CAIDA trace, and we increased the throughput of the original trace, which is much lower, by increasing the number of flows, but without altering the number of packets per flow. So in this case, switcheroo reaches about 31 millions of insertions per second at maximum rate. So this experiment shows that the switcheroo supports millions of insertions per second and scales linearly with respect to the input throughput. Indeed, the limit of 50 millions of insertions per second is due to our testbed and not to limitation of the system. So switcheroo requires recirculation to guarantee some properties, and one may wonder if this increases the end-to-end latency and degrades the overall performance. So in the next experiment, we ask how many times are packets recirculated. To do so, we measure the number of recirculations of each packet, and then we plot the percentage of packets that recirculated a certain amount of time. We still consider 32K entries and 100 gigabit of input traffic. In the one packet flows, most of the packets recirculate one time to perform the insertion, and a small amount recirculates 2 times due to collisions on the ordering data structures. In the due to packet flows, as expected, 50% performs an insertion, and so it recirculates one time, and 50% is forwarded without recirculation due to a successful lookup. And in the best case, so 8 packet flows, 80% of the packets perform a successful lookup, and so it is forwarded without recirculating. So we also measure the end-to-end latency in the same setting, and we report the average by the number of recirculations. And in the no-recirculation case, the latency is in line with the baseline of our testbed without switcheroo. And we notice that for each recirculation, there is an increment of 1.5 microseconds in the latency, which is a reasonable value. Okay. So in conclusion, switcheroo supports millions of insertions per second with limited recirculations and a reasonable overhead in latency. And also consider that this implementation spans 2 pipes, so some of the latency is introduced by recirculating packets between 2 pipes. So before ending, the last question that we want to address is any packet delivered out of order, so not satisfying the packet ordering guarantees? To do so, we run switcheroo by varying the cuckoo table size, and we measure the percentage of out-of-order packets. So in this experiment, we only consider the 8-packet flow traffic pattern, since it has enough packets that could be reordered during transient states. And by removing the ordering data structures, a percentage of packets is reordered, while with the full switcheroo, the implementation is able to guarantee packet ordering in each scenario. So switcheroo effectively guarantees packet ordering. So in conclusion, in this work, we propose switcheroo, which is the first system that implements a key-value data structure entirely using data plane primitives. Switcheroo formally guarantees consistency and per-flow packet ordering, which are required by any packet processor. In our evaluation, we demonstrate that switcheroo achieved performance that are orders of magnitude higher than the state of the art with reasonable overheads, and it pushes the barrier of what is possible to offload into programmable switches. So I'm at the end. Thank you for the attention. And if you have any question, I'm happy to answer. If you want to check our public implementation, please follow the QR code. Thank you.
Thank you. Any question?
Okay, so back at maybe slide 81, 82. Sorry, you got some results and they look really nice. But I was
This one?
wondering, yeah,
Okay.
but I was wondering, so were these experiments conducted independently of each other? So just one packet flows, just two packet flows, just 8 packet flows?
Yes.
In which case, what was the one of the a naive interpretation of what you've done? I could imagine that a mixture of packets, eventually you're actually accumulating more and more latency for all packets in the system. And so what's the collateral damage of for example, a bunch of different sized packet flows on each other rather than just on themselves?
Okay. So yeah, we tried to consider this case by running the 8 packet flows trace, basically, because in that case you have more packets of different flows that like concurrently arrive at the switch and do the insertions or modifications. So that trace should potentially cover this scenario that you are explaining. But we didn't test with different packet sizes. Yes, this is something that we could do as future work. Yep.
Thank you for the great talk. I'm referring to slide 69. So you're saying that you're trying to solve the consistency and packet ordering issue with some auxiliary data structures. So I was wondering whether there are cases where there could be collisions that happen in your auxiliary data structures itself that we should break your guarantees here.
Oh, okay. So you mean, sorry if I reinterpret, you mean if the collisions inside the tables could break this property, the ordering? Well, as you saw from the evaluation, we did the experiments on these by varying the table size, and it never happened. So there should be no case. The only thing that could happen in the worst case is that you have interflow ordering. So if you have different flows that collide on the same entry, what could happen is that someone is not does not require the ordering, but it's still reordered. But if you saw the impact, it's not that much.
Any other question?
Yeah. Thank you, very, very interesting, and congratulations. Going back to the evaluation that you have shown, I think it was around slide 81 again. You write there that the input is 100 gig. Have you tested it also with full throughput through the switch where you have more than the 100 gig? So
Sorry,
when you do it, so you write that the input is 100 gig. Is
yes.
that 100 gig total or 100 gig per port or across all ports?
No, this one is 100 gig per total.
So have you evaluated it with full throughput through the switch?
Yes.
So and what was the throughput in this case when you had also the recirculation?
I think for having more than one gigabit per second, we used more recirculation ports, because in the worst case you fully utilize one of them, and so you need more ports to handle the traffic for the other ports, basically. And we reported only the 100 gigabit because it's like the base case. So when you are using one port, but the behavior should not change when you have multiple ports because they are independent, basically. No, if you have multiple input ports, you have multiple recirculation ports, so they are independent. I don't know if this answered the question.
The overall 3.2 tera entering the chip. What is the overall throughput of the chip?
Yes. Okay. So what? Oh, okay. So okay, no, we didn't test with the full throughput because we didn't have the cables basically to test it. Yes, in the future we plan to test it, of course. Yes.
So the takeaway is Marco can buy some more cables. Okay. Yeah. Thank you very much, and I think we can move on. And thank you again for your talk.
Thanks for the introduction. So hello everyone, I'm Xu Liu from Xi'an Jiaotong University. And today I'm going to talk about the modular data plan verification for compositional networks. And this is joint work with my advisor Peng Zhang and Haoli Wenbing Sun from the Xi'an Jiaotong University. So unlike the classic network built in a layered architecture, today's networks are composed in a more flexible way. For example, the cloud provider virtualizes VPNs on a physical network for multiple tenants. And these VPNs are layered atop this underneath network using technology named NVO3. And these VPNs are also can be bridged together to achieve the communication across the network. Similarly, with the ISP networks, the customer sites in the different region can be connected using tunnel based on MPLS or SRv6. In an organization campus network, the different department networks can be virtualized and connected on demand using protocols like VXLAN, NVGRE, or IP-IP. Although the composition makes networks more flexible, they also make the network more complex. To understand this, let's take a look at a concrete compositional network, a data center network, which use VXLAN to virtualize two VPNs. Here we should have a physical network containing four routers and two servers. To get this network to work, we should first configure the BGP and OSPF to ensure the reachability in the underneath network. Then we create VPNs by configuring VRFs and virtual network identifier on the routers. And then we create tunnels to connect these VRFs by configuring BGP eVPN. After the VMs created on the server, we should connect the VMs to the VPN by configuring VLAN or AND sub-interfaces and configure the map between the traditional VLAN to the VXLAN. And if we want to make the two VPN communicate, we should configure a static route between the VRFs. After all this, we also can configure the group-based policy and the access control list to ensure the secure connection. Besides of the complexity in the configuration, the packet forwarding behavior are also complex. For example, if one VM wants to talk to others, it should forward the packet between the overlay network and the underlay network several times before reaching the destination. For example, if VM1 want to talk to VM3, even these two VMs are hosting the same server, but it should forward the packet first to VRF because these two VMs are belonging to different VPNs, and only F can forward packets between VPNs. So if a packets are getting passing to the through the tunnel, it will get encapsulated in a few new packet headers, such as the destination IP to identify the tunnel endpoint in the underlay network, and the VNI to identify the VPN, and the group ID for secure policy. And when the packet arrives at VRF, it should be matched the group ID to ensure the secure group policy. And if it get permitted, it should then get forwarded to the VRFG. And VRFG, it experiences a similar process from underlay to overlay, eventually reach the VM3. So with higher complexity, it raises the chances to configuration errors, which will potentially lead to network incidents. In recent years, we have witnessed a lot of network outages due to configuration errors. According to this configuration, these network outages have had international impacts, resulting in significant economic losses. And according to a survey done by the Uptime Intelligence, the configuration error is the primary reason that caused the network incidents, which up to 30% of all network outages. So to prevent the network outages, both industry and academia have proposed a data plan verification, hoping to automatically detect the configuration errors and improve the network reliability. So most of the existing data plan verification analyze the packet forwarding behavior using a notion of equivalence class. Generally, they have 3 steps. The first is to extract match action rules for every device from configuration files or FIP tables. These rules can be IP forwarding rules, ASIC rules, or others. The second is to partition the a high-dimensional geometric space composed of packet fields into equivalence class. Each equivalence class is a set of packets sharing the same forwarding behavior across the network. For example, if a packet have only 2 fields, the port and the destination IP, we will partition the equivalence class in the 2-dimensional rectangle. And the third step is to construct a forwarding graph. The graph, each edge labeled carries a label indicating the equivalence class that can allow to pass through this edge. So with this forwarding graph, we can analyze the network. We can check whether this network violates users' intention by traversing this forwarding graph using any graph search algorithm. Although the existing data plan verification are fast, but when applied to the compositional network, it will have a problem named EC explosion. For example, if we have a VPN1 that forwards the packets matches destination IP, then each distinct IP will be partitioned into a separate EC, resulting A, B, and C. Suppose we have another VPN which will forward packets match group ID, then it will double the number of ECs. Imagine we will have more such component network with more extra fields, the EC will explode. In our experiment, we show the state-of-the-art EC-based verifier analyze only 20 VPN composition network. It will have more than 260,000 ECs. So our contribution is to address this problem, and our key idea is based on the observations. We have 2 observations. The first is the forwarding behavior inside each component network is closely coupled. For example, if we have the rule changes on one node in one component, it will affect a large portion of the nodes about their property. If we have a rule changes on E, which to drop the packets destined for VM2, then all paths to VM2 via E will be blocked. The second observation is the forwarding behaviors between components are loosely coupled. It says if we have to another component, then the rule changes on E will have no affection about the properties in these 2 components. So this observation encourages us to a modular verification named decompose and merge reasoning. It consists of 2 stages. The first, we will decompose the network into several modules according to its packet field. Then we will recursively perform the local verification for each module and merging of the verification properties. After all modules are verified, we can check the network behavior is violate the user's intention. In this example, we can separate the verification for VPN 1, VPN 2, and the underlay. And the EC will not explode. This is because each local verification only partitions the EC in a limited, fixed, and a small space of network header instead of a super high-dimensional geometric space. The challenging with decomposed merge reasoning is to achieve two goals. First is to ensure the correctness of the merging. Suppose we want to check the reachability between VPNs, say from VPN 1 to VM3, from VM1 to VM3. Straightforward is to pack the VPN and the VPN 1 module and the VPN 2 module into one module. In this module, we can directly check the reachability. But since this module composes two modules together, it will increase the complexity in the local verification. So it is correct, but inefficiency. This will violate our second goal, is to maximizing the decomposition. However, if we remain the decomposition of the VPN 1 and VPN 2, we cannot check the reachability between the two VMs. So this decomposition is efficient but incorrect. This is because such decomposition overlooks the composition relationship between networks. So the question is, can we have the best of both worlds? The answer is yes, and we propose three techniques to address this problem. The first is a core graph, which we will use it to capture the layering composition. For example, we remain the decomposition of these modules, but we create edges from the VPN to the underlay. This is because these two VPNs are layered atop the underlay through tunnel technology. It indicates that if we will analyze the forwarding behavior of a tunnel, we should depend on the reachability status on the tunnel endpoints. And as I mentioned before, such decomposition will miss the static route from VIFF to the VIFG, which bridging these two VPNs together. But as we know that, we can create a bridge module that models this forwarding behavior between two networks. And in this module, if we know all the internal reachability between the other nodes and F and G, we can locally check the reachability from VM1 to VM3. Luckily, we know the internal reachability can be locally checked in the VPN module. So we just propagate this reachability results to the bridge module. In other words, the bridge module, the local verification of the bridge module depend on the reachability results of the VPN 1 and VPN 2. So to record this dependency, we create the edges from the bridge module to the two VPN module. With this core graph, we organize modules in a hierarchical architecture. So this allows us to analyze the whole compositional network in a bottom-up way. First, we will locally check the reachability in the underlay and the group-based policy module. This process is identical to existing data plan verification, which consists of 3 steps: extract rules and partition ECs and traversing the forwarding graph. Eventually, it will output the reachability inside these 2 modules. In the second round of local verification, we shall look at the forwarding behavior in the VPN 1 and VPN 2. But since VPN 1 and VPN 2 depends on other modules, the rules will catch not only the physical rules that we can extract from the device, but also the virtual rules derived from the local verification results of the underlay and group policy. For example, the first virtual rules is from the GBP module. It indicates that the group-based policy allows the packets with source IP of 10.0/8 to pass from E to F. And the second indicates the reachability in the underlay network between the two tunnel endpoints. So it can also follow the usual data plan verification steps by partitioning ECs and traversing forwarding graph and output the local verification results. And finally, we will analyze the reachability in the bridge module. This also has virtual rules, but all the virtual rules indicates the internal reachability inside VPN1 and VPN2. Here we derive the reachability from VPN1. It's between VM1 to VIF, and the VPN2 is the VIFG to VM3. Also, it can locally compute the ECs and the forwarding graph and eventually compute the reachability between VM1 to VM3. So about the evaluation, first we proved our correctness by prove the soundness of and the completeness. Both proof is based on the mathematical induction on the module hierarchical level. Details can be found in our paper. In terms of the expressiveness, we have the property, we can check, and the property that can be checked. The property can be checked is almost the reachability related property, such as reachability isolation and loop freedom, black hole freedom. And the property cannot be checked, or meaning the path related properties, such as load balancing, mode path consistency, and waypoint. However, we can support to check path related properties by adding new attribute to the local verification results. This work will live as our future work. In terms of performance, we run two experiments. The first is the experiment on a real data center network. This network is constructed on a spine leaf topology with N leaf routers, N VPNs, and 20 VMs each VPN. So in this experiment, our algorithm can scale to 500 VPNs, but existing EC-based can only up to 20 VPNs. This is because they run out of time or memory overflow due to EC explosion. Besides, we compared our method to non-EC-based verifier. We are 100 times faster than it. Second, we show our number EC has a 99.8% reduction in number of EC. The second experiment is run on the layer network. This network is synthesized from the Katra paper, and we test the scalability by changing the layers and the nodes in each layer. So our method is can complete all experiment in less than 100 seconds and is 20 times faster than Katra. In conclusion, compositional networks are pervasive, flexible, and complex. Existing verifiers are not scalable on compositional networks, and we propose a modular verifier based on decomposed merge reasoning, and we prove our algorithm is correct and is scalable. Thank you for your attention. And we take
Thank you very much. Any question? Okay, I'm gonna start with one. So let's start from the assumption that I know almost zero about network verification, so probably my question is a little bit, but I have read, like in the past, even some blog posts from companies, like for example, Meta proposed this Flash algorithm for verification of a data plane, and I wonder how can you put in context your solution with some production level system, if you have seen them, and if you can provide me an insight on when is better to use your solution and when the other solution fail, basically.
Okay. Our algorithm actually leverage the existing data plane verification. So in our experiment, in our implementation, we leverage APKeep or also a EC-based verifier. As you speak earlier, the Flash is also an extent of work to the APKeep. So when we use compositional networks, each network is a small network. We can use existing data plane verifiers to analyze it. But when it compose, we cannot use existing verifier to do the whole verification. So we need to compose it. And this is when we use the framework we proposed today.
I see. Yeah, thank you. Any other question?
Hello, thank you for the talk. You mentioned that your framework cannot verify load balancers. I want to know what is typical for the load balancers that doesn't fit your framework for verification. Thank you.
Okay, we cannot check the load balancing because we need to count how many paths from the source to the destination. But currently, we only focus on the reachability. So we focus on the three tuple property, like from the source, destination, and the packet that can reach from the source. We didn't record how many paths are available between these two. So we only we can support the load balancing. So we just need to record how many paths are available. So we can change the three tuple results to a four tuple. So we can support the load balancing. This work is considered in our future work.
Any other question? Then we can thank the speaker.